Hello students, today we are going to learn resolving power of telescope. Now as we know, telescope are used to see the distance object. Suppose if I am taking for example we can say star, or any planet. If you will see, if you want to see, then you will use telescopes over there, isn't it? So now if we are observing stars, these are luminous point objects, isn't it? They are self-luminous points, or point objects, and they are far off from us. Thus, their diffraction pattern are arrayed disks. Okay, as these stars or luminous objects far off, we consider only the angular separation between the two and not the linear separation. After drawing a diagram, we can get the clear idea of that. Okay, so first of all, we will see what is the resolving power of telescope. That definition we will write here. So we will consider here this, the resolving power of telescope is defined as the reciprocal of the smallest angle subtended at the objective by two distant point objects which are just resolved. So from the definition it is very clear that this is the reciprocal of the smallest angle subtended at the objective by the two distant point objects. Okay, so we are considering here not the linear distance but the angular distance. Okay, so for this purpose we will draw the diagram first, so that we can get the clear idea how the telescope works, and we can find then the resolving power of the telescope. So here now I'll try to draw the objective. What is objective? The lens used in the telescope which is near to the object is known as objective. Okay, so here now the rays are very far. Okay, so rays are far, the point objects are very far, stars are very far, so we consider the rays which are coming from the first star, and these are, for our convenience, only 3 we are taking here at the middle, and 2 are at the extreme position of the aperture of the objective. Now here we will see this is the axis we have drawn here, of this, and which gives the diameter of the objective. So here I'll write this is objective. Okay, it is objective, and AB, we mention the objective as AB here, and this is the diameter of this, and that is given, suppose is equals to capital D. So these rays are coming from this, all these rays which are coming from the first star that are mentioned here, these are the rays. Okay, so now I'll show you. This is the first ray, this is the second ray, and this is the third ray, which are coming from the far source somewhere here at a infinite distance. Okay, now somewhere here the second star is there, okay, very near to the first one. So we are showing the rays coming from the second star, and mentioning those with different colors. We are showing those rays which are coming from the second source, and this is suppose the second star from which the ray is coming, and we are showing those rays. Okay, here somewhere the second ray is situated, second source is situated. Now here I'll show you somewhere here. This is the second source, okay, and this is the first source, very near to each other. Now I'll show you again these three rays from the second source we are taking, and this is the middle one by here it is making some angle with the previous one, and that angle we are denoting by theta, and the second ray we should show from the source, same source, and it is now here making some angle theta again, and the third source which is making here the angle theta. So these are again parallel to each other. So here we can show this is the angle between these two, and this is theta, and this is again theta. Okay, so now when these rays, orange color we will show, and red color, so red color rays, when they are coming and entering to the objective or lens, then what will happen, this will go straight here and reach up to this point, and at the focus here it will be like this, and they will join together at this point. So the point will obtain over here, and that point we are showing by the first image here, that is let us consider I. Okay, now these rays, it should be these should be red in color. So I'm again taking red color. Okay, so these are the first source we are showing here. This is the first source from those which the light which is coming from the first source, that we are showing by a red light. So this is the image where at I1 we are getting, and now this is the second source from which again we are getting the rays, and will reach here somewhere at this point. without deflection this ray will go from the principal axis, and then these are the two rays. Okay, so here now I'm showing this by arrow. All these are arrows, with arrows we are showing. So now we are getting the another point, and here the image is formed, that is suppose I dash. Okay, so now the path difference is there. Here this no path difference is there, because this line and this line is of equal length, we can say. So there is no path difference at this point, and we will get the diffraction pattern. Now if we will consider this one, so there is a path difference between these two, isn't it? And this much path difference is there, and that is equals to, so let us consider here the M point. So here I am taking M point, so BM is the path difference, BM is the path difference. Okay, so now this is the small angle, or the smallest angle subtended by the two point objects at the objective. So this is called the smallest angle, that is theta. Now we know that reciprocal of this is gives us the resolving power, and that is equal to 1 upon theta. Okay, first of all we are going to find what is theta. So here we'll go next and we'll write here. Now suppose as the star or luminous objects far off, we consider only the angular separation between them, that I told you just now. Now let us consider these rays are coming from the far distances, so they are parallel to each other. Now you can see here in this diagram, so all these are parallel to each other. When they come and enter to this objective, they will converge over here, and we will get the images I1 and I2, I1 and I dash. Okay, now if Airy theory is applied, okay, if the Airy theory is applied, to Fraunhofer's diffraction pattern. Fraunhofer's diffraction pattern. Okay, now let us consider here, if you are getting this these 2 points over there, images will get here the diffraction pattern. That diffraction pattern I am going to draw here. So let us consider here, this is the here we are getting the first this will be the maximum intensity we are showing here, okay, due to the second source, and this is the minimum intensity of it, and on that minimum intensity now we are getting the maximum of this. So it will start like this, and so in this case now the minimum of the first is coinciding with the maximum of the second. That time these points or these sources are called just resolved. Okay, this is the just resolved condition. Okay, so if it happens, then we are applying the array theory and to the Fraunhofer diffraction pattern, and we will get here the path difference, and path difference is equals to now how much? It is a bi dash minus ai dash. Okay, and that is given as 1.22 lambda by this. If we apply the arrays theory with to the Fraunhofer diffraction pattern, so if D is the aperture, of objective AB, so we can write here this is equals to path difference, and that is equals to, now here we can write bi dash minus ai dash is equals to d into theta. Okay, and path difference is this, and so it is given already, that is equals to 0.22 lambda. Now from this equation we can write here theta is equals to, and theta yes, theta is equals to, we can write 1.22 lambda upon d. So this is nothing but the angular separations we got, and by definition of resolving power, we know that resolving power of telescope is reciprocal, isn't it? Reciprocal of theta. So RP of telescope is equals to, this will be now 1 upon theta, and so this will go upside down, so it will be d upon 1.22, and in this way we found the resolving power of telescope. In the next lecture, we will solve the numericals depends upon the resolving power of microscope as well as the resolving power of telescope. Till that time, study well and have a nice day. So just go through it. Whenever the question will arrive on the resolving power of telescope, you have to write the first definition of it, and then we will go through the diagram, and depend upon the diagram you will write these equations. First of all, you will find the path difference, and from the path difference you will get the theta's value, and as soon as you get the theta's value, you can find the resolving power of telescope, because it is inversely proportional to it. Thank you.